We left off with the idea that the dienes and dienophiles are capable of coming together in what's called a Diels-Alder reaction to produce six-membered rings. And this is very powerful, and you can see in a sort of synthetic sense where this can take you. You can make alkenes, you can make dienes from different simple elimination chemistry. You can put the two together, you can make a six-membered ring, and then you're off. Away you go. You can manipulate the functional groups, and you can make all sorts of different things. So be aware of the fact that you're looking for a diene, two pi bonds next to each other, and you're looking for a dienophile, something that's activated with maybe a carbonyl attached to it. And the mechanism for this is well understood now. It's not fitting into the same paradigm that we've used with pluses and minuses and nucleophiles and electrophiles. It's a bit different to that, but it works very well. On the bottom, you can see here that activating the system with an electron withdrawing group makes a big difference. On the left, you have very high temperatures and you get a low yield. On the right, you get a very high yield at room temperature or around there. And that's because of the fact that, as I'll show you in a second, the bonds, or the orbitals involved in the interactions to make these molecules come closer together when you put the electron withdrawing group on there. In terms of things you ought to be looking out for, these are the types of things that we'll use as the dienophile. The diene will be obvious. It'll be a cycle with two double bonds. It'll be an acycle with two double bonds. You're looking for carbonyl groups, or in general, electron withdrawing groups to be able to activate the pi bond to make it a good dienophile. We left off with this slide, I believe, where we talked about the idea of the stereospecificity of this reaction. If you start with a cis dienophile, those two X groups end up on the same side in the six-membered ring. That tells you it's a concerted process. You don't have any free rotation in single bonds as you go through to that product, and that gets trapped. So you start with the cis, you get the cis outcome. You start with the trans, you get the trans outcome, right? And that's telling us now it's a concerted process. Be careful here on the homework. There's a chapter 17 homework and a quiz out there. We're not having a sit-down quiz this week. We want to spend more time talking about this material in recitation. But you can see now at the bottom, the pi bond is left over. In this example, you're starting with an alkyne with two pi bonds. You use one of them as the dienophile. You are left with another one. And keep an eye on that in terms of the possibilities then you've got with those pi bonds to be able to use them. Well, we mentioned that the dienes, if they're acyclic, they can rotate. The rotation is hindered in the sense that it's slower than a normal single bond, but you can rotate around these single bonds, and we can get what we call the S-cis and the S-trans type of situation, in which we have the possibility of this now. We need this to be able to do the reaction. If we have this and it's trapped in that form, it won't do this Diels-Alder reaction. Right? So you'll need to have the S-cis. You'll see here at the bottom, talking about the sort of limitations here. The problem with that double bond and that double bond is that they're trapped in the S-trans. And you'll see why in a second that you can't possibly have a Diels-Alder reaction there, because the front carbons of the diene can't approach the alkene at the same time. And that will give you no reaction. So some little details here. We'll finish the Diels-Alder reaction off very quickly. In recitation, we'll show you how to practice to draw these things, because it can be quite tricky. Show you some shortcuts, and then we're into chapter 18. So a very good diene is the cyclopentadiene, right? You've got this thing in a five-membered ring. It's trapped as the S-cis. It can't become the S-trans. There's no free rotation in that cycle, so that won't do this type of reaction. In this example here, I've got the S-cis trapped completely, and it's not going to do anything else. The orientation of that double bond right there, what is it? Cis or trans? Trans. So you should find out in the product that X and X are on opposite sides. In other words, one is up and one is down. Now, some terminology. What direction is that pointing down? Think of this as a six-membered ring. What type of direction is that? Axial. Good. And what type is that? Equatorial. Now, I've got to be careful here, because we've talked about the fact that typically axial is bad and equatorial is better, and not necessarily the case here, because we don't have any one-free axial interactions. If you think about the opposite side of that molecule, in this case we have the hydrogens are not pointing straight down, so they're not axial. They're kind of pointing out into space, so they don't interfere. So when we talk about the endo and exo idea in a second, we don't have to be concerned about that interaction, because it really isn't there. Okay, now let's think about this little stereochemical issue. I've seen it on MCATs, PCATs, stuff like that. I've seen it on GREs. It's something that people should be aware of in the future. In this reaction, we're keeping it simple. We are starting with a very good diene, the cyclopentadiene, which is trapped in the S-cis. Everything is going for that reaction in that system. And we are starting off with a highly activated dienophile, which has two electron withdrawing groups attached. This reaction will go well, and it will go in high yield. And we're doing the 4 plus 2. And if you wanted to draw a mechanism, you would take 2 pi electrons from there, and you would attack that carbon, and you would take 2 pi electrons from there, attack that one, and then the last two end up as the retained pi bond in the product every time. And every time you get a six-membered ring. Well, what's happened now is we've got two isomers. And the two isomers here, one is called endo and one is called exo. Now, the one I've always, this is the one that's easier to understand. This is the one that's pointing out, away from the molecule, exiting the molecule. So that is the exo isomer, and this is the endo isomer. And it turns out now there is a preference for the endo isomer in many of these reactions. You will get more of that product. And again, be careful here. There are no protons over here that are pointing straight down, so there's no problem like this. There's no diaxial interaction really concerned about here. So that's not such a worry. Get rid of that. It turns out this is favored, and we have to think about why that's favored. We'll have to worry about the orientation of the groups as they come towards each other in the transition state, and then that will lead, since it's only one step, it's really got something to do with the transition state energies. It's only the one step to give the product, so that's where the differentiation will be. So in this example, we can see at the bottom a typical way of drawing these things. You've probably practiced these things with the bicycles last year. We can practice them again, and you can get good at this because they are very useful materials. Now, here is the argument for why you get more of one than the other. And it's all to do with the transition states for the two different processes. In this example, there are no carbocations, there aren't multiple steps, so we can't talk about Markovnikov or stuff like that. It's simply the relative energy of the transition states going over a barrier. And I think my next slide will show you that, okay? In this example, we're saying that the preference for the endo is actually a lower energy in terms of the transition state, and the preference for the exo is actually a higher energy state. And they might have a little bit of difference in terms of their relative stability at the end, but this is all governed by the height of the transition states. Now, these pictures that we go back to here, we can see the possibilities here of two orientations in which the diene is lining up either on top of the alkene or it's lining up to the side of the alkene. That's the difference. It's just simply the way they've approached each other in different directions. At the top, we get the endo type of system in which we're taking the diene system and landing it on top of the double bond. And the carbonyls are underneath the diene, right? As opposed to the bottom, where we're adding the diene from the top and the carbonyls are pointing away from the double bond. And that will give you the exo isomer. So it turns out that the one at the top is more stabilized than the one at the bottom. And some people believe this, some people don't. I think it's fine in terms of an explanation. But what you've got here are the p orbitals of the diene. And they are organized around that cycle. They are electron density, and they are looking to overlap with things. Now, as you start to think about the pi bond forming here, that is going to require formation of an overlap between two orbitals and formation of a pi bond. But the argument is this. If the carbonyls are underneath the molecule, you get this extra little bit of interaction. Okay? You get this little extra bit of bonding that's going to help you stabilize that transition state. And so that possibility now will explain why the molecule prefers to come in from underneath as opposed to outside, and you get the endo system. You can think about it in the product maybe. Maybe this isn't such a big deal, but you can see now that those two atoms and those two bonds, or those two orbitals, are fairly close to each other, and you might get some extra overlap and some extra bonding. Every time you get some extra bonding, it's more stable than if you don't. So the transition states here, you need to be aware of this. You need to be able to draw something like that and to be able to explain why that is better than this system. And it's all to do with something that we call a secondary orbital overlap. The idea that the pi bonds can communicate better at the top picture than they can at the bottom picture, and that leads to the difference in the outcomes. So you'll have a challenge here with several different things. Number one, being able to draw them after you complete the products. Every time you get a six-membered ring, you have to worry about stereochemistry, you have to worry about orientation in terms of endo and exo, and now you have to worry about the reasons why. But be aware it's a very simple system because all we're talking about here is one step. It's a fully concerted process in which you get the two pieces coming together at the same time to give the product. All right? So I think that might show up in one of your labs in the near future. Now, why does this work so well? Why is this different to the systems we have seen so far? Much of what we've done in the last 8-9 months, whatever it's been, has been find a nucleophile with a lone pair and go after something positive that needs that extra help, needs that extra electron density. That's not happening here. We seem to have pi bond going after pi bond going after pi bond. That doesn't seem to make any sense, right? Because you have electron-rich thing going after electron-rich thing. Or maybe not. If you've got an electron withdrawing group on the dienophile, maybe that's a little bit of electron pull. Maybe it needs some help from the diene to be able to form bonds to help to become more stable. Now, I'll go back to this very quickly. And I will start chopping out some of this stuff because it's probably not that important to what you're interested in the future. This was the typical picture we drew for the molecular orbital picture for an alkene. You have two orbitals. At the bottom, you have the pi. At the top, you have the pi star. One of them is full, one of them is empty. That's a typical pi bond, nothing too tricky there. We then moved on to these, which become much more difficult. With a diene, you've got 4 p orbitals, and you've got to worry about all the different molecular orbitals you can draw. If you have 4 p orbitals, you get 4 molecular orbitals. And we did this last week in which we said, okay, starting at the bottom, This is the best situation. Everything is bonding. There is communication between all of those atoms, and we have the strongest situation, the most stable situation. We then move up and say, all right, what happens now is that this now is going to have one pi bond at one end, one pi bond at the other end, and they're not talking to each other. They're not conjugated in this sense, and they're not communicating. That's a little bit less stable, but it is still a bonding situation. And then we went above what we call the 0 point. The 0 point is at this point where the p orbitals will be independent p orbitals before they overlap. And then if they come together in different situations, we could end up with a situation like this, in which one end is completely not communicating to the middle, and the middle is not talking to the right-hand side. That's not a good situation. If you were to populate that orbital, you'd maybe have a radical. The radicals aren't stable, we know that, and that's why it's so high. And at the top, you get the worst possibility of the lot, in which no communication whatsoever, and that's then going to be the pi star least stable, and we very rarely use that, right? We very rarely use that. We know it's there, but we don't need to use it. Now, definitions from last time. If you're going to put electrons in these orbitals, you're going to want to put them in bonding orbitals if you can. And in this situation, because we have 4 orbitals with 4 electrons, I can put 2 at the bottom, no problem, and I can put 2 here, no problem. I don't have to put any electrons in an antibond. Yeah? I don't even have to put them in non-bonding orbitals at the 0 point. I can just put them into bonds, and that's good because we get good overlap. And we had some definitions. The highest occupied is what it says. It is the highest energy orbital that has electron density in it, the highest occupied molecular orbital. Very easy to spot. And the lowest unoccupied is the one above that. And those are the ones you're typically talking about. We don't need to talk about the bottom, and we don't need to talk about the top. It's the middle ones that we're going to talk about. So once we've got those definitions out of the way, we can think about how this is going to work for the communication between the diene and the dienophile. How do these orbitals come together to make some sense without being able to use this plus-minus sort of paradigm that we've played with for the whole 2 terms so far? So be aware, one of these things is the HOMO, and this one we really don't talk about. Okay, that's the best situation. It's stable. We're not going to use that. What we are going to use is the HOMO, and we're going to bond it with the LUMO of the other piece. If you want to learn more about this, take an advanced class. It's interesting stuff. It can explain pretty much everything we talk about in the class instead of using those arrows, right? But the arrows are much more convenient, and they tend to be much more popular, and it does work very well. So in this example, I need to form a bond between these 2 molecules. I need to form bonds, I should say. So I need to think about electrons and orbitals overlapping with each other to form those new sigma bonds and form a new pi bond. And we have to get this thing started. We have to have an initial interaction between the 2 molecules. We know it's concerted, so it's basically this piece comes together with this piece. We have to be concerned with what the electrons are doing and what the orbitals are doing in that process. So in this example, it doesn't make any sense to me that this should interact with this. I don't have any electron density in either orbitals. If I'm going to make a bond, I need some electron density, right? So I'm not going to use those 2. I'm not going to use these 2 because they're both full. If you attack one with the other, you're attacking basically a nucleophile with a nucleophile. That's no good. So what I'm going to try and do here is overlap this orbital with this orbital in the initial sort of process to be able to get this reaction to work. So basically, if I wanted to draw some sort of indication of that, I'm going to do that. Now, why do we need electron withdrawing groups on the dienophile? Well, it turns out it lowers the energy of this. Okay, it lowers the energy of this and brings it closer to this, and so you get a better overlap. With that in mind, we can look at the Book's representation, and we can think about how this works, and just mention briefly the whole idea of the Woodward-Hoffman rules and the frontier orbital approach theory to show you where it comes from. So in this example, I'm taking the molecular orbital that contains 2 electrons from the diene. It's the highest energy of the 2, and I'm using those 2 electrons to get this thing going by pushing those electron density into the lowest unoccupied molecular orbital of the diene, of the dienophile. And so now I can think about bonding. I can think about electron density being pushed towards the other piece from the diene, and you can think about the bonds start to form. Now take that a bit further. We're not just bonding one atom with one atom to give one single bond. There's a whole bunch else happening in this system. You're forming 2 new single bonds and a new pi bond at the same time. If you look at that product in the bottom, you can say that this single bond has been formed, this single bond has been formed, and that pi bond has been formed. So there's an awful lot going on that isn't just one interaction. What we can see at the bottom is a very simple but very, there's a lot more to this if you're interested in the future. The interaction between those 2 pieces is allowed. Okay? It's allowed because the atoms and their orbitals are in phase with each other. They're the correct phase. And when we represent phase here, it's either blue or red. Why is this high energy? Because the red is not communicating with the blue. They're out of phase. They're not overlapping. If you were to overlap them, like here, the red, the blue and the blue, those 2 parts are in phase. That's why you get a bond. So one is constructive interference, one is destructive interference. Now at the bottom, Michael, Okay, let's be careful now that we've got 6 electrons total. This system has 6 electrons total. 2 of them are in this pi bond, 2 of them are in this pi bond, and 2 of them are in that pi bond. Okay? So what's going to happen is some change. I think the key word is change. Things are going to have to change. Some things might have to change their hybridization patterns, and change their shapes, and maybe change their phase. Some things are going to have to change. So what will happen in this situation? Why is this particular orbital allowed to occupy or to interact with that particular orbital? Because at the front, when you bring these two pieces together, the lobes are actually in phase. Okay? This lobe, this red, will interact with this red, and this blue over here will interact with that blue over there. None of those others make any sense. None of those others will actually match up to form you a bond. So in this example, we've certainly got that potential here for a bond, and we've got that potential here for a bond. So that's where the sigma bonds come from. Now, to form the pi bond, we've got to think about other interactions at the back, where maybe this thing falls over like this thing comes up like this, and they overlap to form a pi bond, right? They change their sort of direction. And you can think about 2 electrons in this bond and 2 electrons in this bond being pushed around so that ultimately you get a bond there. Now, I'm not going to spend an awful lot of time on this because, number one, we missed a day, and number two, it really is beyond the scope of most of the people in this class. If you're a chemist and you want to learn about this stuff, we can spend months on this, right? But for most people, it's going to be, here's the background to it. It is different to what we've seen. It isn't simply nucleophile, electrophile stuff, but this is important, and it does make sense. So what we've got at the end of this is we've got to put some electron density in there. There's the new single bond, there's the new pi bond, and we have a 6-membered ring. Okay? So with that in mind, I'm going to skip this. Then I'm going to go back and show you why I'm skipping it. Don't worry about 2 plus 2. If I have to get rid of anything at this point, it's going to be this. Don't worry about what's called a 2 plus 2 cycloaddition. When I write quizzes, this won't be on there. When I write the exam, it won't be on there. Okay? Read it if you like. It's very interesting because it's photolytic chemistry. It allows you to think about how you can manipulate a system using light. But in terms of synthesis, we're not going to worry too much about it. So get rid of that. Get rid of this, which is the explanation for it, the 2 plus 2. And then get rid of that, which is the transition state for that 2 plus 2. So I think I've chopped out 4 slides there. I was always going to chop this stuff out. Again, if it was a chemistry class, not happy with that, Piers? Okay. If it was a chemistry class, you could spend months on this, and if you want to take 5821 in the future, we'll cover this stuff in great detail. Take intermediate organic in the future. We're not going to cover that, and we're not going to cover 1710. All right? So let me say that again. I'm not covering the 2 plus 2 stuff. I'm not covering the 179, which is electrocyclic reactions, and I'm not covering 1710, which is sigmatropic reactions. They're pure chemistry. And I want to get to the end of the semester and talk about biological stuff. I want to talk about polymer stuff. I want to talk about the application of this material. And I want to have a couple of weeks to do that. Now, what did I just try and summarize? I'm interested in the 4 plus 2 cycloaddition. I'm very interested in the Diels-Alder reaction. You should know how it works. You should have some idea about its stereochemistry, some idea about endo-exo preferences, some idea of how to draw transition states and explain why one is better than the other, and be able to draw products. Okay? This is very powerful because look at that. All of a sudden, I can build these marvelous sort of architectures in which we have these 3 cycles joined together simply by putting together 2 flat pieces. This is very, very important stuff. Is that clear enough? Okay. Now, again, this is a transition. We're getting out of the, we've done with the spectroscopy for a while, apart from this. We're trying to get into the benzene chemistry, which is way more important than 2 plus 2 cycloadditions, I think. And we need to talk at the end of this chapter about something called ultraviolet visible spectroscopy. Now, if you're wearing anything colorful, you are doing ultraviolet visible spectroscopy as we speak. All right? So the idea now that conjugation leads to the potential to promote electrons from one energy orbital to the next, from one energy level to the next. And that's easier than it sounds. This is going back to the NMR stuff. Remember we had 2 energy states? One was lower, one is higher. In this, we're talking not about nuclei. We're not talking about bonds as we were talking about in infrared spectroscopy. We're talking about electrons. And it turns out now that that gap between these 2 energy levels, one occupied and one occupied, we can jump that gap. We can put energy into this system and make an electron go from the lower state to the higher state. We can excite it. We can go from a lower energy state to an excited state. And to do that, we need some light. Now, as we work our way through to bigger molecules, we see that light comes into the visible region. But in biology, biochemistry, organic chemistry, we usually do this in the ultraviolet region, right? So you can't see it necessarily. And you've all done this in the lab when you took an ultraviolet lamp last year and you put the light on top of a TLC plate, and all of a sudden you saw spots that you couldn't see before you did that. Is that right? You remember doing this one? Now, does anybody remember what those materials had in common? Every one of them had something in common. They were all solids. Some of them were colorful. But what did they contain? What organic piece did they all contain? It's been a while. They all contained a benzene ring. Okay? And a benzene ring is what's called a chromophore. Right? Chromo, think about light, chromatic, chromo, and chromophore. We're going to see now that if you have the right amount of conjugation, you'll be able to do this bumping of the electron in the ultraviolet visible spectrum, and you'll be able to see a response. So what we're doing here is looking at the gap. If this gap is very large, maybe it doesn't work. If this gap is small, maybe it tells you something about the energy levels and their sort of relative energy. So in this case, all we're doing is maybe think about TLC. Think about UV. Think about the visible spectrum. We're in that region right now. Incredibly powerful tool for us as organic chemists, which we use to tell if we have something like a chromophore. Do we have a benzene ring in our molecule? Beyond that, we have all sorts of other techniques that are more powerful. But if you're a biochemist and the NMR spectra of your material is incredibly complex, maybe ultraviolet visible is better. It helps you. You can tell what sort of protein you have, and you can tell what sort of DNA you have. So what we'll do here is very quickly take one of these electrons from this lower energy orbital and throw it up or bump it up to this antibond. Now that won't be stable, right? That won't be stable and it will come back down, but you can measure the gap, you can measure the distance, and that's what UVVIS tells you. And it tells you all about conjugation. Now, having done NMR spectroscopy with doublets of triplets of quartets, there's a UV visible spectrum. Not an awful lot going on. Okay? Not an awful lot of any use there. Maybe underselling it there, but as an organic chemist, that doesn't tell me very much. We do see a signal, right? An absorbent signal at a certain wavelength. At the bottom we have wavelength, and in this case we have the bump or the absorbent on the left. It's not an infrared spectrum, it's different. It only contains usually one or two simple signals, but it tells you if you have something in there that is conjugated. So if you want an idea of what UVVIS is about, it's about conjugation and being able to detect it. So we have a scale, wavelengths, nanometers, and you see that these absorbances are measured as such. In terms of where it's happening and sort of how this tells you about conjugation, here we have three different situations. One of which is diene, butadiene, that we've already dealt with. Next one is the triene, and next one is the tetraene. Now, is it fair to say that they are becoming more highly conjugated? Yes, you're adding more pi bonds to get more communication. And if you were to draw the molecular orbital diagrams for these, because you have 4 molecular orbitals here because it's butadiene, and you have 6 here because it's a hex, a triene, and then 8 because it's an octatetraene, you're going to have to draw these pictures for each of them. And what you should notice on those pictures is that the gap between this one is higher than the gap between this one, because that's what we're doing, is promoting an electron from the lower orbital to the higher orbital. So what it's going to take is less energy to do that, and then lower energy, longer wavelength. So we'll see now that if you can measure that wavelength, you can tell about conjugation if you know some basics. So in this example, the lowest of this will be here, and ultimately, as we add more double bonds, maybe that gap gets so small that we're now into the visible spectrum, and we can see it as a colorful material. Not a lot here in terms of huge understanding. Here we have some actual numbers. Okay, the lowest wave number here, or the wavelength I should say, 217, and the highest one there is 290. And those numbers, like its signal on a C13 or an NMR spectrum at various places, will give you an indication about what type of system you have in your molecule. Now, there are rules out there. I think it's the Woodward-Pfizer type of rules that you can use to actually build this up, and you can come up with some very, very accurate numbers for how this works and what to expect in a molecule that you make. And that was brilliant stuff back before NMR spectroscopy was important. But this has kind of gone by the way. When this was put together, when these rules were put together by Woodward, that was the 1940s, 1950s, before NMR, and now we have NMR, so we don't really need to do this. So usually what we do with a UV visible spectrum is think about, is it a chromophore? Does it contain a benzene ring? But again, it's been superseded by other systems in which we can definitely tell we have benzene. And all we use this for in my lab now as a synthetic chemist is trying to find the products in a reaction mixture on a TLC plate. Exactly what you did last year. So really UVVIS, you'll find it useful again in biochem if you take that. It's very simple in terms of the output because there's only usually one curve, and you should be spending more of your time concentrating on the C13 and the NMR spectra because that's way more useful and way more important. So with that in mind, we can extend this and you can get into some crazy conjugated systems which become really, really highly conjugated, and you can get into colorful systems. And most of the dyes that are used in clothing contain these highly conjugated systems. And at the top you've got a very, very highly conjugated system. You can see here, this is not, but all the way along here is. And so you can expect that to have an absorbance in the visible region of the spectrum. And then down here, where's this found? Have a guess. Carrots. How do you work that one out? Yeah, it says carotene. And I think this it derives, or it's close to vitamin A. And you can see here a whole bunch of conjugation. And what color are carrots, Pierce? Don't get this one wrong. They are orange indeed. So now you've got to the point where you can actually see these things. So again, it's a whole science in itself. You take biochem, you learn a lot more about that because it's more relevant to them. Anybody want to say anything? Michael? I don't know. That's how much I know about UVVIS. I don't know. And again, let's keep it in context. Since I was born in '65, so that was about the time NMR spectroscopy became useful. And I was raised on NMR because it's much more useful than this. But before that, how do you tell what you get, what you have? So they had to work out the UVVIS ideas. I don't know the answer. Last example here, just to whet your appetite for later, for biochem. This whole idea of conjugation and vision will be very important. If anybody's into optometry, obviously that's going to be important. You'll see this system when you get to biochem, and the idea of how we absorb light, and we can tell different colors from each other. And we'll see later on when we do this type of chemistry that that's a conjugate that conjugates and makes it highly conjugated. There's lots of conjugation going on there. And we'll deal with that when we get to the biochem stuff at the end. Now that's the end of that chapter. It's a pity we weren't here Friday because I'd much rather be in the next chapter, but that's it. But it's just a gentle introduction to double bonds next to each other. Double bonds next to each other show up all over the place. This chapter is much more important. It's much more relevant and I think much more interesting. And what we'll start off by doing here is looking at some pharmaceuticals that contain what we call a benzene ring. Now this benzene ring is something that you will spend a lot of time worrying about, and you'll spend a lot of time thinking about mechanisms for how it can do its chemistry. We have all sorts of possibilities on here. Anybody who works in a pharmacy who's got any interest in pharmacy or medicine, you should look at these things and think, all right, these are things I should know about. Lipitor, right? Incredibly incredibly top-selling pharmaceutical, $1 billion in terms of its sales. And you can see the double bonds and the pi bonds and the benzene rings. And these benzene rings often are just flat pieces, right? They're flat and they're non-polar, and they're used to sort of guide these molecules maybe into a protein and to interact with a protein. I don't know what some of these things are. Zyprexa contains a system right there. Norvasc on the top right again has a chlorobenzene system, and down here Nexium, all kinds of different things, right? These are all top-selling pharmaceuticals, and they're all based on this platform, this benzene ring, this aromatic system. Now, aromatic doesn't mean anything anymore. Aromatic, when people were first trying to categorize these things, some of them smelled really nice. Benzene itself smells quite sweet. It's very bad for you, but it smells sweet. And then, unfortunately, there are many aromatic compounds that just stink. Right? They don't have nice aromas, and some of them you can't smell. So this is a term like organic chemistry itself, which is kind of irrelevant these days, but it is still used to categorize molecules of a certain type. Aromatic compounds. And we'll find that aromatic compounds are very stable. Right? You're going to have for the most part, 6 p orbitals in a cycle, or 6 pi electrons in a cycle. And that will be a good stabilized system. We'll develop a method to understand that and to be able to predict it. When you see a molecule you haven't seen before, is this aromatic or not? And what it means, it doesn't mean does it have a smell anymore. It means is it stabilized in terms of its molecular orbitals. So with those in mind, a very quick sort of look here. I like this picture. This is what happens when you burn coal. Now, all politics aside, when you burn coal, it isn't a very clean process, regardless of what people will say. Because when you burn coal, this is what you produce. And the picture of coal at the top is just showing you it's an incredibly complex sort of matrix of single bonds and aromatics and sulfur and all sorts of different things, right? We've got all sorts of different materials in there. And when you burn this stuff and you paralyze it, you get all sorts of different outcomes. Now, benzene is highly carcinogenic. You're advised to avoid benzene these days, right? You try to get away from benzene because it's so nasty. Toluene isn't so bad, right? Toluene we can metabolize. If you're unfortunate enough, toluene is used as paint thinner to wash paintbrushes with. And if you're unfortunate enough to actually ingest some toluene, you might be okay, because we do have a mechanism in our body to get rid of stuff like that. We can oxidize this here, make it a carboxylic acid, which makes it more polar, and then we get rid of it in the urine. So you can get rid of that stuff. You can't do that with benzene. And naphthalene. Where is naphthalene used the most? Where do you know naphthalene from? Mothballs, right? It has a nice smell, and in that case, it's a solid. So what you get is and here's what they won't tell you. Many other aromatic compounds which probably aren't very good for you, right? And they get into the atmosphere, and all of a sudden we've got problems. So we get aromatics from various sources, and you have to be an expert in this very quickly. Nomenclature. There is, again, historical nomenclature and systematic nomenclature, because these compounds have been used for hundreds of years, and they've been formalized over the past 150 years, particularly in the pharmaceutical industry and the pharmacy business. They have common names that everybody knows, and they have systematic names that you can work out. Again, most of this is up to you. And if I ask you a nomenclature question on an exam from now on, it's usually a lead into something else. You're not going to get 10 points anymore for just naming things. It's going to be know the name of it so you can actually do chemistry with it. So some of these are obvious. Ready, Pierce? Chlorobenzene. Good with that? You haven't seen nitro yet. Nitro will be fun. Nitro can go boom. All right, TNT, trinitro-toluene, we'll build that. This can be useful, it can be dangerous. Ethylbenzene is fairly obvious. Just work out what the radical is and then call it benzene, ethylbenzene. Now, the ones that you haven't seen before that you should know, down at the bottom, toluene. If you went to the store, Home Depot, Lowe's, wherever, and you asked for a bottle of methylbenzene, they'll just look at you weird. You're not from around here, are you, boy? Toluene, that's what everybody calls it. Toluene. Phenol. Phenol shows up a lot. We'll see a lot of chemistry of that stuff in the near future. Anisole, methyl or methoxybenzene. You could call it methoxybenzene if you can't remember, but its nickname is anisole. Aniline is very important. You'll see quite a bit of that. Aniline, right? You could call it aminobenzene if you're stuck, but it's aniline. Benzoic acid you've seen before, at least twice in the labs, so you should know what that is. Benzaldehyde is fairly obvious, benzene ring, aldehyde attached, benzaldehyde. Acetophenone, different one, right? This is an aceto group. There's a ketone, acetophenone. You could also call it methylphenylketone if you like. On the right-hand side, styrene. Where do you know styrene from? What does that remind you of? Polystyrene, right? And polystyrene has been used for years as a plastic for things like packaging, and it's a big problem now because it's not very dense. It doesn't sink in the ocean, and it sort of floats around and ends up on beaches, and it's a mess. But these are all compounds that you'll need to know the name of. So know those as soon as you can. Other ways of drawing these things, other ways of using this as a substituent. Remember in the past we did a system where if it's simple enough to call a molecule a chloride, do so. If it's not, use chloro or bromo instead. In this example here, let's say this part over here becomes really, really complicated, and you're going to have a hard time naming it as a benzene derivative. Then we've used phenyl, not phenol, phenyl. That tells you have a benzene type radical attached to something else. I've seen this type of notation. I don't use this myself, but if you see it, this is what it means. I prefer to use that or to draw out the rings themselves. And what is that symbol? Is that phi? What is that? Phi. Phi, phi, fo, fum. Phi. Are you messing with me? Is he? I have no idea. Anyway, I don't draw that. You're welcome to draw it, but I don't. Over here you can see now the use of this in terms of substituent patterns. It's a nice shortcut to be able to do that. So nomenclature isn't so tricky until you get into the substituted patterns. And you get into monosubstituted and disubstituted and trisubstituted, all the way up to hexasubstituted. And we think of benzene as a platform. It's a flat piece that can project 6 other groups out into space. Yeah? It's a flat piece, and you've got 6 valences, all of which are pointing out in a plane into space. And this is very useful as a medicinal sort of chemistry type of idea. In this molecule, you're quite welcome to call it 1,2-dimethylbenzene because that's what it is. You could also call it ortho. Okay? Ortho we've dealt with before. You put this together with the infrared spectra that we've done. You look at the bottom right of the infrared sheet or the spectroscopy sheet. You now have some ideas of what these things look like. And that extra bit of information helps you work out substitution patterns on a benzene ring. If you move to 1,3, you're quite welcome to call it 1,3-dimethylbenzene. But you might also see it called meta, right? In this case, xylene. Xylene is a di-substituted. It's a cousin of toluene, if you like. It's one extra methyl group. And in this case, the meta substitution pattern is meta-xylene. And then if they're completely far away from each other on the opposite sides, we call it para, which is the 1,4 situation. And you've seen stuff like this. Which of those will have the least number of signals in the C13 spectrum? The para, right? It's highly symmetrical. Which one will have more signals, this one or this one? Probably the one in the middle, yeah? The one on the left has got some heavy symmetry right there. So down at the bottom, you can call that 2-nitro-anisole. Anisole, you can call it 2-nitro-methoxybenzene if you like. You know, we can do it that way. And over here, meta-bromotoluene, parachlorobenzaldehyde. It's fairly simple if you practice some of these things. And the book and Wiley Plus have some good things to practice on the Orion system. Make sure you're okay with the names. You'll see these again. Any of you got any ambitions of professional training in medical school or pharmacy school, you'll see all those things again. Polysubstitution. This is more realistic now because these are the things we'll make. We've got 3 different groups on here. And we've got a parent on the top. We've got phenol as the parent. And then the 2 bromo groups. Remember, what was always the most important functional group in nomenclature? Alcohol. And what was the least important? Alkyl groups and alkyl halides. So that kind of makes sense here where they sort of, they're subservient to the actual phenol itself. So numbers should be okay. This is always number 1, as it was for cycles. The OH group is always number 1, and then everything else goes relative to it. Down at the bottom, I think we're okay with that. In this case, we go left to right, or counterclockwise, I should say, as opposed to going in that direction because you get smaller numbers. Nothing more difficult than anything we've seen. Ready? Are you sitting comfortably? All right. Let's start benzene chemistry. We've got 2.5 weeks of this, through this next exam into after spring break. It's a lot of stuff. People thought about the structure of this thing for years. It took generations for people to work out what exactly benzene was, why it reacted the way it did, and what its shape was. And we have 2 ways of drawing this. And this is, you can see here, 60 years difference for people to actually nail down and be happy with what benzene looked like. That was a long time. In 1866, Kekulé, a Belgian chemist who lived in London for some reason, he decided that benzene was a mixture of isomers. And those isomers were always interconverting. Because what we're going to try and explain here is this phenomenon. Which should be longer? The sigma bond or the pi bond? Sigma. Sigma is usually longer than pi, right? Turns out they're the same. If you measure those bonds, they are the same length. Now, this was before resonance. This was before delocalization everybody was comfortable with that. If you physically measure by whatever technique that those bonds are identical, then you've got a problem because you're drawing a pi bond next to a single bond. And if you want to take this to an extreme, if a single bond is longer and a pi bond is shorter, surely this molecule should look like this. Yeah? It isn't. It's symmetrical. It's a perfect hexagon. So, trying to work this out, what was going on? Kekulé, 60 years before Robinson, said, okay, maybe it's one of these equilibrium systems where molecule A is turning into molecule B by the pi bonds moving around, by the pi bonds changing their position. And if you wanted to try and draw a mechanism for that, maybe it's something like this. Yeah? Now, that was okay for a while, and people will still draw Kekulé structures. People will still draw these structures because we need some electron density, and we'll use one of those pi bonds to go hit something, to go initiate some type of reaction. But it was never fully, it was never thorough. It never quite worked for everybody. So, 1920, Robinson, English chemist. What else was he famous for? Anybody remember? something you all love and you will never forget in your lives. He's responsible for these things. All right, so Robert Robinson. Nobel Prize winner. He came up with this idea that benzene probably is delocalized. This idea now that the pi system is completely delocalized over the whole 6-atom system. So it isn't this, and it isn't this. It's somewhere between. What is the difference here between the systems? That was thought to be equilibrium, where things were changing from one to the other. This is now delocalization, using that resonance arrow. So that will help explain the shape of the thing, the reactivity of the thing, or the stability of the thing, and also the mechanisms that it undertakes. That's an important slide for anybody who's taking anything organic related in the future. Isaac Napoleon Pierce. Yes. Yes. This picture became popular. Okay? This is a way of taking those two pictures and drawing a hybrid, if you like. It looks like a hybrid. It's not perfect, but it works. You don't see so much of that in organic classes because we have to push arrows. And I don't see any bonds to push arrows with. You will see it in biochem and biology classes. When they're trying to do shortcuts and they just want a benzene ring right there, you'll see that. It's very quick to draw. So the Robertson sextet explains how this is completely delocalized. And we'll put, I'll put up some models in a second and show you how this works from a more sort of detailed perspective. But we now had the problem solved. Benzene is not a bunch of alternating pi bonds and single bonds. It is a completely delocalized pi system built on top of a sigma framework. So it's an extension of what we just did with the conjugation stuff. We did the dienes. That was communicating across the system. It was conjugated. We went to the more complex trienes and tetraenes and stuff like that. They were more complicated, or there was more communication there. So what I want to try and get through before the end of today is to try and get you the idea that benzene has two chapters. It's unique in that sense. It gets two chapters of its own because its chemistry is very varied and very important. This has been something that's been hugely important to the chemical industry for 100 years at least. It still is in terms of producing chemicals of various uses, and also for things like dyes. Most of the dyes that are in your clothes are going to be benzene based, and also pharmaceuticals, as I showed you on the first slide. You've got to know something about benzene chemistry. So to get this started, here is a very simple series of experiments that you could run yourselves. If you take an alkene, and you did this in lab, I believe, when you made 4-methylcyclohexene last year, one of the tests was to take a drop of bromine and to add it to the product that you got and see if anything happened. The starting alcohol would not react. That was the control. But if you had made the alkene successfully in that lab, phosphoric acid, 4-methylcyclohexanol, boil it away, distill it, purify it, and then you did this test. What color is bromine? It's deep orange. It's a deep orange color. And if you have an alkene present and you put a drop of bromine in there, initially the solution is orange. What happens to it over time if the alkene is present? Now, you've got to be careful with the difference between clear and colorless, right? It is clear, because you can see through it, but it's colorless. It goes colorless. And why is that? Because the bromine is being consumed. Why is the bromine being consumed? Because it's reacting with the alkene. We did this with the bromonium ion. We talked about the trans-stereochemical outcome. That's a reaction you know well. But it is a very simple colorimetric test, if you like, for an alkene. That works. Now, here's the problem. When people were scratching their heads about what benzene really was, that looks like a pi bond. That looks like a pi bond. That looks like a pi bond. Is it an alkene or not? Nowadays, we don't think it's an alkene. It's not a simple alkene at all. So one of the measures of that is that it doesn't react with bromine. And you know Br2 is a weak molecule. You'd like to break it if you can. That's not going to happen. This is a very stable system that does not react like a regular alkene. And what we'll do here for the next 5, 6, 7, 8, 9, 10 lectures, whatever it takes through the week after spring break, is get happy with why this is the case, the fact that this molecule is super stabilized, and you have to help it out to make it react. In other words, you're going to have to put something in its place that is very reactive in order to make this thing want to react with it. And that's a huge amount of chemistry. So we're going to say that benzene is way more stable than simply 3 alkenes. Other examples, if you take an alkene and you add hydrogen to it, you can reduce it quite easily, and you can get 100% of this product. You can do that often at room temperature, you can do it at atmospheric pressure. Well, this at the bottom tells you different, right? You still need a metal catalyst, but 100 atmospheres? That's not easy. The engineers might be, a piece of cake, right? But that's not something I can do in my lab very easy, I don't think. And 150 degrees C doesn't sound very pleasant. So basically, you have to really work hard to be able to hydrogenate benzene, and that's an indication that it's very stable. It's much more stable than it would be if it were 3 alkenes. This picture is very similar to what we talked about with butadiene. All you're doing here is setting up experiments side by side in which you have one alkene, cyclohexene. And if you add one molecule of hydrogen and you get to cyclohexane, you can measure the energy released, 120 kilojoules per mole. If you then went to 2 alkenes, if you didn't know anything about conjugation, you might say, okay, one of these things is worth 120, so 2 of them should be worth 240, right? And you don't get that number. You get less than 240. In other words, this is a bit more stable than if these two were isolated double bonds. So what's the difference? Where's the difference in the energy? That's the conjugation energy, right? That's the benefit you get from being conjugated. Now, theoretically, if you went from this system up to the 3 alkene system, surely if 1 double bond is worth 120, 3 double bonds should be worth 360. Nowhere near. Nowhere near. All right? It's down here. It's way more stable. It's even more stable than the diene itself, even though there's an extra pi bond there. Because everything's communicating, everything's conjugated, everything's delocalized. So that experiment is important. You should be able to explain that experiment back and understand what it's there for, to show you that benzene is way more stable than you might expect for simple alkyl type molecules. Stop me at any time. Ask questions. Tell me about your weekend, whatever. The Coley. Yep, the diene. Yep. You're thinking now, yes. If you made it into an isolated diene, chances are you get close to 240. Absolutely, good. But because they're conjugated, a little bit more stable, and there's a measure of that stability. It's an experiment that shows you that. Now, Wednesday. I'm going to talk about this now, and then Wednesday we'll get back into it. In this example, we're going to have to worry about pi bonds and molecular orbitals again to understand the basis of the chemistry here. Because ultimately, I'm going to build a 6-pi system, and I'm going to populate it. We're going to ask where are the orbitals and where are the electrons. That is something you've seen multiple times this past week. Adjacent p orbitals can either overlap or not. They can form a pi bond, or they can form an antibond, pi star. That's for a simple pi bond. What we did for butadiene was put 2 of these things next to each other. Now we're going to put 6 of them next to each other, or 3 of them, 3 pi bonds, and put them all next to each other. Here's the system. This is a picture that you should be able to draw. This is a system in which it exactly illustrates what I'm after here. This p orbital is parallel to that p orbital. They are neighbors. They should communicate and form a pi bond. But now you have a situation where this orbital is also in the same orientation with that one. They're next door to each other. They should overlap. And that happens to every atom around the cycle. They can bond with neighbors on both sides. We couldn't do that with the dienes. We can now do that in a circle with the triene system. And that gives us benzene, which is super stabilized. And on Wednesday, we'll draw these pictures and try to explain them. Now, I'm going to stop there. I'm going to